Okay, let's talk about your forces notes check number one. The way I graded this was I was looking for 10 correct or kind of correct answers. You'll notice there are 15 questions on this. So you had 15 chances to get 10 things correct. However, what I saw was a lot of misconceptions in your notes, and that's fine. But we need to get those things cleaned up and cleared up before we move forward. So here's what I'm going to do. I'm going to give you this full-size piece of paper. This is more like a notes summary because you got some things wrong. There's some things you don't understand. And even though you might have gotten a 100 on the notes check, because I graded very, very graciously, you don't have the level of understanding that you need to go forward. So in order to get the 100 that I put on that notes check, you're going to listen and you're going to clear up those misconceptions and you're going to complete this notes check as I go through this lecture. When you show me this at the end of the video and you show that you now understand these concepts, I'll write that 100 in the grade book. If you do not complete this, I will not. If you scored less than 100, and there were two scores that were less than 70, here's a chance for you to bring those scores up to 70. So think about it as kind of a recovery for you. Or if you got a 100 because I graded it graciously, here's your chance to get that 100 and show me that now you understand everything. So first of all, let's move right along here. Definition of a force, we're going to keep this pretty simple. A force is a push or pull. A lot of you started talking about things about changing motion and other things. No, let's keep this simple. For the context for us to figure out our problems and our situations, just remember that a force is a push or a pull, and it is always measured in newtons, named, of course, for Sir Isaac Newton. Now, the definition of inertia, a lot of you got correct. The definition of inertia is a tendency of an object to resist a change in its motion. The tendency of an object to resist and here's a big capital word, change in its motion. And that's important because some of you were mentioning about things that weren't moving or getting things moving. If something is already moving, it has inertia. And if you want to change its motion, you've got to overcome that inertia. Things that are at rest, like this rock, it doesn't want to be moved. In order to move it, you have to overcome its inertia. Because all objects, no matter what they are, they resist having their motion changed. And that's where forces come in, because you have to apply a force to overcome that inertia. Now, the one thing that you guys didn't mention about inertia, and I need to make sure we're clear on this, is how do we measure it or how do we quantify it? Well, inertia is 100% a function of mass. More mass equals a greater inertia. So these two rocks, this rock has a greater inertia than this one because it has more mass to it. It's a lot harder to get this rock moving than it is this one. And we know that the bigger things are, the harder they are to move. That's inertia. But remember that it's about change in motion. If this rock is already moving and this rock is already moving, it's a lot easier to change the motion of this rock than this one, because this one we already said has less inertia. That'd be like, think about a baseball game. If I were to throw a wiffle ball at you versus a shot put and you hit it with a bat, well, shot put's heavy. It's hard to bat a shot put because it would have a lot of inertia. Things like Nerf balls and wiffle balls that are really lightweight, low mass, it's easy to change their motion because they have a low inertia. How would we define tension? Most of you got this correct. It's a force exerted through a chain or a rope or something similar, a wire, a string, whatever. A lot of misconceptions, a lot of problems with normal force. A lot of you started talking about the ground. And you had some mention of perpendicular sometimes, but not others. But the wording was not necessarily correct. We need to clear this up. The normal force is a force provided by the surface of contact. And a lot of you had the idea when we did our first lab that, hey, this object is sitting on a surface and it has weight going down. There must be some force going back up, and that is called the normal force. The normal force is exerted at 90 degrees from surface of contact between items or objects. A lot of you wanted to talk about the ground. You don't have to be sitting on the ground to have a normal force. This pen has weight. Weight is a force going down. The table is pushing back up. Well, the table's not the ground. Now, there's a normal force on the table because the table's resting on the ground, although not really. I'm on the third floor here. So it's the floor of the third floor that provides the normal force. You got to get out of the habit of saying it's the ground that causes the normal force. And more importantly, some of you mentioned the 90 degrees, some of you didn't. Some of you said 90 degrees from the ground. And that's right in a situation like this if it's lying on the ground. But the surface of contact could be a ramp, because the ground and the world is not necessarily 100% flat. If I have an object on a ramp like this, the normal force is 90 degrees from the contact. Something like that, which means it is not 90 degrees to the ground. There's a big difference between those, and that's what we need to clear up. The concept of equilibrium. A lot of you started talking about forces here and saying, oh, all the forces on an object are equal, and it is not moving. That is 100% not true. Something can be moving and be in equilibrium. What equilibrium means is that motion is not changing. There's the key. It doesn't mean that it's sitting still. It means the motion is not changing. Consider a box sitting on a table, and it's just sitting there. Its motion is not changing. It's just sitting there. It's got a force pointed down, and the table pushes back with an equal amount of force, and it's just sitting there. However, something can be moving, and its motion is not changing. Something that is like a car, say, on cruise control, going in a straight line. Got a car, and it's going forward, let's say at a constant 30 miles per hour in a straight line. Velocity is not changing. Therefore, that is a situation of equilibrium, where the motion is not changing. Now that leads us into our Newton's first law. Newton's first law says that an object at rest will remain at rest, and an object in motion will remain in motion until or unless a big capital words here, net force acts on it. Okay. Now we'll get to that concept of net force next. But an object can have forces acting on it and it remain the same. That rock, as it's got forces. I had to put tables pushing back, the weights pulling down. And it will always sit there so long as the forces remain the same, pushing up as going down. If I took an impossibly large size rock with a lot of weight and I put it on this table and it broke the table, that would be an example here of Newton's first law, where the motion is then changing because the force of the weight of the boulder, say, on the table was greater than the normal force that could be provided, and so the table gave way and the rock moved down. You have to have a net force. You can have a force acting on an object and it stays in constant motion, or it doesn't stay moving at all. You have to have that word net force. So, what is meant by net force? A net force is the sum of all forces acting on an object. You can have a net force of 0. If I have a force going up of 5 and a force going down of 5, a force going to the left of 3, a force going to the left of, or the right of, of 3, well, the sum of all those forces, 5 up, 5 down, 3 left, 3 right, the sum would be 0, would be the net force. Now, if I change this and I made this 5, now I have a net force of 2 to the right. Notice when I talk about a net force, forces are vectors. I've got to say which direction the net force works because it is a vector. So a net force can be 0, it can be 2, it could be a negative, because if I say this way is the negative direction, my net force could be negative. But keep in mind that the net force is the sum of all of the forces acting on an object. If the sum of all the forces, if the net force is 0, motion doesn't change. You have to have one force bigger than another in order to change the motion of the object. The formula for calculating weight, most of you got this, must be expressed in kilograms. Well, the question is why? Why kilograms? A Newton is equal to a kilogram times a meter per second. That's how you get the unit of kilogram. So your mass has got to be in kilogram. And we know that G is expressed in meters per second squared. The purpose of a free body diagram is to show or visually represent all the forces acting on an object. A lot of you were starting to do this incorrectly on the lab. And that's why we're going to clear this up now. I'm going to show you how you draw a free body diagram. Typically, you draw just a box. And you draw the forces as acting usually from the center of mass. You represent vectors with arrows. And keep in mind, the size of the arrow that you draw represents the relative size of that force or that vector. So let's say I have something like this. I have a weight coming down of 5 newtons. And this is a box sitting on a table. I know it's not moving, therefore must have a net force of 0. All the forces are equal. So that means there must be a 5 Newton force going up. When you draw these, it is important to draw the arrows about the same size in this case, because that shows this push or pull is about the same size as this one. We're not going to take out a ruler and measure them exactly, but they have to be somewhat similar. That if I look at it, oh, okay, those are equal, but they're in opposite directions. This here was the normal force, that there was the weight force. Typically, if you know what the force is, if it has a name like the normal force or the weight force, you do label it as such. So for the true-false questions, these were good thinking questions that showed me how well you understood these concepts. And that's why I graded this very leniently. But a lot of you got these incorrect, and let's clear those up. The normal force has no maximum value. That is false. Here's why. Imagine you have a table, and on that table, you put a 5-Newton box, and the table can push back and support a 5-Newton weight. That's the normal force. Well, the normal force can't be infinite, because if I put an elephant on top of my table, maybe has a 1,500 Newton of force, the table cannot provide that much normal force, and the table would collapse. The motion would change, because now we have a net force. We have a force that's bigger than the net force outside the normal force that can be provided by the table. So to say that the normal force has no maximum value is very definitely false. Does the normal force change? Yes. On my table, if I have a 5-Newton box and I have a 10-Newton box, in this case, the normal force is 5, and here it's 10, and it can be anything in between, but it is not infinite. There is a maximum value that can be provided by a surface, even the ground. People will sink, or an object can sink into the ground. Think of like the mud. A muddy ground can't provide enough normal force, and therefore your motion changes and goes into the ground. An object will act at rest until a force acts upon it. False. That rock has a force acting on it. There is a weight force pushing down. The table's pushing back up with a normal force. It will stay at rest until a force acts upon it. Well, there's forces on it, and it's still rest. It's still resting. What's missing here is the word net. An object will stay at rest until a net force acts upon it. In other words, there is a bigger force in one direction than another. So in this case, I start to push on the rock this way. Now there's a bigger force that direction, and it moves that way, because now there's a bigger force one way than the other. That's a net force. The normal force acts perpendicular to the surface of contact. That is true. A lot of you guys, you said true here, but then up here with your definition of normal force, you didn't have it correct. It is about the surface of contact, not the ground. If the net force is 0, the object is in equilibrium. That is true. And what does that mean? It means the motion doesn't change. It doesn't mean that it's not moving. It just means that the motion does not change. So at this time, you can bring this to me. You get a done stamp just for doing it, and you're going to put this in your notebook kind of as a summary to have. And at that point, I'll give you back your notes check that you took, and I'll record the grade that you got on it.